Hi, everyone. Thanks for coming to this talk. My name is Vikram. I'm an intern here for the next week or so, which means I'm really stocking up on the naked juice. This is my colleague, Viral. This is a bunch of slides from the research we do in our group at UCSB. And that's the campus. The talk is about lessons that we've learned when measuring productivity of programmers. And specifically, we're looking at the programmers that write high performance code, so parallel code in UPC or things like that. But as we go on till the end of the talk, you'll realize that a lot of the stuff you can do even in serial code that you write. A small clarification about the abstract. We don't personally have 30 years of experience programming. What we were trying to say was that in computing, there is about 30 years of parallel programming experience. This reminds me of a bunch of good lawyer jokes, but I think I'll keep them for the questions. So onward to the talk, let me tell you about the motivation for this work. What are we trying to do, and why is it important? Machines are becoming cheap, everyone knows that. Machines are becoming fast, everyone knows that too. And we know that because performance of hardware is fairly easy to measure. You run a bunch of programs on tomorrow's machines, hopefully they'll be faster than today's. And that's how you get to know that hardware performance is getting increasingly better, but also hardware performance is getting sidelined by programmer performance. This is certainly true of serial programming, and I don't think anyone can dispute that now. Machine code was replaced by assembly and onto Fortran and C, and now everyone uses Python, Ruby, Perl, what have you. And even if the code that you write in Perl or in Python is some X slower than machine code or hand-tuned C code, we think that the gain in human productivity is worth it. We're willing to make that change. We're willing to write it in a language which allows us to get the program written quicker, so a 10x difference doesn't really matter that much. But the thing with human productivity is that it's really hard to measure. How do we compare the productivity of a person using Eclipse to him using IntelliJ, for instance? People live and die by camps, and there's not much you can do to convince them. Or how do you judge a group of fairly qualified Lisp hackers from a group of fairly qualified, say, Python hackers, right? We don't really know. Moreover, it's not only the final outcome that's interesting to us, but also the process by which you solve the problem. If the problem is to write a program to do something, you're not only interested in how long it takes you to write that program, but what were you doing while you were doing it? What was your process of solution like? For instance, if two people take the same time, but the first guy spends it all in waiting for his machine to boot up, then we know how to speed it hum very quickly. We know how to boost his productivity fairly quickly. This is not a new problem. A lot of people have looked at it before. There are a lot of interesting studies in literature comparing serial languages. There is also very good anecdotal evidence about productivity of programmers varying a lot based on which language you come from. Most famously, Paul Graham's articles about ViaWeb are quite familiar, and they've convinced many of us to start learning Lisp and Scheme again. Yes, I see Michael there agrees. However, what we really lack are metrics. We say that, well, Scheme is better, Lisp is good, it lets me write stuff on the Palm Pilot because it's so small. But we don't really have a metric which lets us compare stuff. We do have some metrics. Source lines of code is a metric a lot of people use, but it measures, so for people who are not familiar with source lines of code, it measures how many lines of code you've written. And it does tell you some things. In particular, it's directly proportional to the number of bugs that are in your source code, because the number of bugs is proportional to how long your code is. It's also directly proportional to how much effort you put in. For instance, you can write your own matrix vector multiplication routine, and you'll have great amount of productivity. On the other hand, you could just know about a couple of libraries which do it for you. So it's a good measure of effort. It's a good measure of bugs. But really, is it a measure of productivity? So you have source lines of code, which is a metric, and you could use it. But the important thing, and I want to emphasize this again, is you want to learn the process by which the programmer came up with the solution. I mean, it's just like computer programming. You want to find out what's the loop that takes 90% of your time so you can speed up that loop to get the most gain in productivity. So if compilation's only 2% of the entire process, you don't want to speed up compilation. You don't want to say my language compiles to object code faster, because it doesn't really matter. It's only 2%. So we're interested in the process. We're interested in the workflow of the programmer. As part of the HPCS program, we are involved in finding out what effect the language and the platform have in high-performance code development. And in order to gather this data, we perform classroom studies in a class taught by John Gilbert at UCSB. Both of us are TAs for that class. And the goal of this is to figure out what kind of machines, high productivity stuff should be written in, what languages should it be written in, should it be done on a Linux cluster with MPI? Maybe. So let me explain a bit of the setting that we are working with, a bit of what our hamster cage looks like. It's a graduate level class. It's called Parallel Programming something, something, something. It's taught over a quarter, which means it's 10 weeks of time, but you really get about 8 weeks, give, take all the holidays. It's required for a CSE emphasis, but it's not required for a graduation. So a lot of the people who are taking this are taking it out of interest, not because they have to. It typically starts with about 20 people and reaches stable equilibrium at about 10. There are 3 homeworks. Each homework takes 2 weeks, and there's a project. The project is open-ended, so we don't measure it because there's nothing we know about it. The project is a group project. The classroom homeworks are individual work. Each homework is roughly the same effort. We try hard to make it the same effort. And if we find that students are having a tough time, we kind of scale it down. But at this point, we've got it down to 2 weeks of good effort. And there is a lot of variety. And this is what I want to stress. There are 2 programming environments. C with MPI, we used to support Fortran with MPI, but I don't think we do anymore. There are not too many people writing Fortran and MPI anyway. And we have UPC. We also have a bunch of different hardware. So we have a cluster, which is at UCSB, which is just homebrew. There's an IBM machine in San Diego, and there's a Cray. All right, students who take this class are fairly good serial programmers. They know how to write serial code. They're not newbies, but they haven't done very much parallel programming. They might have heard of MPI, they might have seen a bit of MPI code, but they certainly haven't done very much themselves. They come from a wide variety of backgrounds. They come from CS, mech, chemical engineering, even mathematics. And so we claim that this makes our average case fairly representative of new parallel programmers. It's not just CS people. So while the homeworks are quite small and well contained, the process by which you arrive at a solution to the homework is still representative of what you would do if you're writing real parallel code. So the homeworks are just 2 weeks. You don't use them again ever in your life, most like all graduate stuff you ever do. So the way you solve it, the way you solve these problems is you start with a framework and you say, well, I want to write a conjugate gradient, which parallelizes well. You write some sort of serial implementation of it, well, or something which works in parallel, but not too quickly. And once it's working, you start figuring out, okay, I need to speed it up. And then you go speed up a program. This is fairly representative of how you would write real parallel code. The programs themselves are not representative. You wouldn't write a conjugate gradient. I don't think anyone would pay you for it. But the process by which you would write it is quite similar. Again, homeworks are individual, no collaboration. And all right, so that's the experiments we have. As all good scientists do, we also need to get lots and lots of data from this. So let's look at how we could gather the data. There are different methods you could use to gather data in a study like this. There's a group which is gathering data by asking students what they think they're doing. So there are compile time questionnaires. And every time you compile, it says, so what do you think you were doing? One is I was editing something trivial. Two is I was taking out, I don't know, X amount of time. I was speeding it up. 3 is I was debugging. I found an error in my code. And it's multiple choice. Otherwise, really, you can't do anything with it. If you ask them to write an essay level answer every time they compile, they'll probably stop compiling altogether. And of course, there are shortcomings to this. Partly because all good hackers will figure out how to wrap a call to the compiler in a shell code which answers all the questions for them. But the student himself might not know what he's doing. He might, the definition between debugging and optimizing is hazy for a lot of people. I don't know, was I optimizing? Probably I was. I was doing a bit of both. So maybe I was optimizing. Maybe you might have just been debugging. Maybe your program was not going to run before that. So asking students to answer these questions is, well, it gives you some idea, but I'm not sure if it gives you a great idea. On the far end, what you could do is you could gather all the data there is. You could hook them up to a video capture unit. You just see everything he does, all the mouse clicks, measure their temperature, and all that stuff. And you would get a lot of data. You would get way too much data. I don't know what you'd do with it. So both ends of the spectrum are bad. You probably want to find a sweet spot in the middle. And what you want in the data that you collect is that it should be simple. Simple in the sense that you want to get only the data which is relevant. I mean, you could calculate, or you could keep the guy's body temperature, but is it going to be that useful? We want the data to be effortless for the student, so it shouldn't involve a lot of effort on their part to put in, because otherwise they'll just figure out how to write a shell script. If it involves a lot of effort and the guy is very motivated, and it takes him like a minute to go through this, he'll want to compile less, so you will change the system. There's some uncertainty going on there. And you want the data to be repeatable. If you capture the data and later you decide, oops, I wanted this feature and I haven't got it, there should be a way for you to go back and get it. And the data collection should be robust. I mean, it should work in one classroom experiment. It should work 2 years hence. Other people should be able to use it and stuff like that. Excuse me. And since we were the subjects under test were humans, you have to be careful. It shouldn't impact their grades. You don't want to give them better grades if they answer the questions and stuff like that. So there's some stuff to do with that. Students are given a fairly nice framework that they have to code in. They're allowed to edit only one function in most cases. So everything is set up for them. They have a data generator that we provide. They get the data, and they just have to do the conjugate gradient. At the end of it, they're told, well, it runs. It's correct, because it's easy to verify. So that's kind of nice, because you contain the problem down to the very essence of parallel programming. You don't have to give them the framework. You don't have to have them write the framework. All right, and what we gather from this is every time they do a compile, we get a timestamp on when they did a compile. There's the CVS log, so we know what source code they're compiling. So we can go back exactly to that point and look at their source code and compile it again later on in time and say, wow, that was a correct run, because we can verify it. We also timestamp runs, so we know how often they did runs. And runs are important because if a run takes 5 seconds and it's followed by 2 or 3 runs after that, for different values, for different parameters, you know that the guy is getting timing results and he wants to speed up his code. All right. So with that, I'll talk of how a programmer programs and what workflow they have. The workflow of a programmer can be decided, can be a directed graph where nodes are the activities they're doing and the arrows are their transition from one activity to the other. And a formal model for this is a timed Markov model with nodes representing states and transitions are timed. The timing is important so we know how much time they spent on the node. So if the mean time spent on an edit node is 3 minutes, you know that on the average 3 minutes are spent editing the code. And once we do have such a model, we can change just one variable, holding all others constant. So you can change a variable like, how did the Cray programmers do versus the IBM programmers? Or how did the Unix guys do versus the Windows guys? All right, before I pass out here, I'll turn the talk over to Viral, who will cover the workflows, the models, and our findings.
So thanks a lot again, Vic. That was a great introduction. And so I'm going to describe the modeling process from now on. We've described the experimental process, how we set up the experiments, how you know the kinds of homeworks the students do, the kind of data that we gather, and now comes the part where you actually try to make some sense out of this data, where you say what's going on. And like Vikram said, we're using time Markov models in this case. This is one way to do it, and I'd be open to suggestions from all you guys here. Feel free to ask me questions or interrupt me at any time. I'd rather this be more interactive than just me talking all the time. So just a formal definition, what a time Markov process is for those of you who might not know about it. It's basically a Markov process. There are states of transition. So state A could be edit and state B could be, let's say, run. So we put 2 numbers on each edge transition, which is the probability of transitioning from state A to state B. What's the probability that you're going to debug after editing your code, or what's the probability that you might, let's say, optimize your code after this particular edit, and the time, which is the dwell time. How much time are you going to spend editing before you might debug or optimize, for instance? So this is the framework. So this is basically a time Markov model that we're gonna use for we're gonna fit our observed data to. We have 2 years worth of experiments to look at. The first experiment was in 2005, and just a brief run through of what that was. It was a parallel sorting homework in C++ and MPI. This was the one in which students were asked a question every time they compiled. We didn't trust their answers. So we took all their code snapshots, reran it, and used simple heuristics to assign reasons for compiling. So for instance, if we ran a program and if we compiled it, it compiled correctly, we assume there are no compile time errors. If it compiled, we ran it. If it ran correctly, we knew it's a correct run. If it crashed, there was a good chance they're going to be debugging after that specific run. If the program is faster than the previous run, there's a good chance that what they're doing is optimizing this code. So really just simple heuristics, nothing very fancy, and we put it on this model. So here's finally actually a quantitative model with numbers on it. What's going on in this model? So the students start in the formulate stage. You know, you can't really see what they're doing at that point. They might be thinking in the shower, or they're thinking while they're riding their bike to campus or something. They start programming at certain points. It's a 2-week-long homework, so at some point they start programming, and there are essentially 2 cycles here. So there's the top cycle is what we call the debug cycle, and the bottom cycle is a compile cycle. So just like, you know, imagine yourself writing a code. You know, you write something, you compile it, and maybe you run it, right? And there's a good chance in the beginning it's not going to run. It's not even going to compile. If it does run, you might have to go back and debug it. So you kind of keep doing this until you get something that is working. And let's say you're happy at some point with what you have. At that point, you might say, okay, I'm gonna optimize this program because in this class, students are graded on the performance of their codes. So, you have something working correctly, you go down to the bottom cycle and you start optimizing your code. So let me just point out a few interesting things in this model out here. For instance, if you look at the compile to the test transition, you can only test after you compile. I mean, you have to run your program. So the probability is 1 out there, which is the first number on the edge. The second number is 49 seconds. It means that it's taking on average students 49 seconds to compile their code. This includes the time that the machine spends in compiling the code, as well as the time that it takes for students to get rid of any compile time errors. Question?
What would refactoring fall under this?
Where would refactoring fall here? So refactoring would, for instance, fall in one of the transitions that goes from debug to compile or optimize to compile, depending on where you're doing it. So that's where students are really writing all their code. Okay. Do you have something to say?
So if they're refactoring after the code has compiled and run correctly, so if it's a conjugate gradient and it's run correctly the first time, then we consider them to refactor in the optimized stage. But if it has never run correctly, the program has never produced a correct output, then it's still in the top cycle.
So you raise a very valid point here. I mean, this is a very simple model. This is one student writing one program over 2 weeks. This is not how we develop software. I mean, you typically have to port software, port tools. You have more testing. You might have specs. You might have all kinds of stuff. So this is really meant to be a simple model in which we can think about things without really having too many things going on. Some expected things. Debug to compile, if you look at that transition, it takes 380 seconds for you to get something. It's 380 seconds while you're editing the code, so that's approximately like 6 minutes there. When you're optimizing, it's like 10 minutes. So again, I mean, that's not completely unexpected, right? I mean, you'd expect that, when you're working harder, you're not just getting rid of bugs, but you're actually thinking at a higher level, maybe trying to make your code faster. The run times, if you look at the run to optimize and the test to debug arrows, the edges out there, you're spending about the same amount of time running your code in this case. Okay, there's not much going on there. The key point I'd like to point out in this diagram is if you look at the test state. So from the test state, you can either have a working program and go into the optimize cycle, which is great, right? I mean, you want to be in the bottom cycle. You don't want to be in the top cycle. Or you could go back to debug, your program didn't work correctly, or basically essentially go in the top cycle, in the topmost cycle. There's a 95% chance that every time you run your code, you're going to go and debug your program instead of making progress and compile your code, optimize your code. So when we are designing new programming languages, what we really want to do is maybe make a programming language that probably allows us to stay in the bottom cycle, spend less time debugging, more time doing useful things. So question, I mean, if you're using, instead of C and MPI, let's say you were using a dynamic programming language, if you're using something like Python for parallel programming, or one of the newer languages that the vendors like Sun, IBM, and Cray are proposing for HPCS, would this matter? How different would the numbers be? Just to give you an idea of some kind of sensitivity analysis from these numbers, it turns out that if you can change the timings, which is the dwell times, let's say I write a new language in which it turns out that instead of 380 seconds, it's going to take you only 90 seconds going in debugging. Is that really, is it a good thing? And it turns out that at least with these time Markov models, what you really want to do is affect the probabilities on these edge transitions, not the timings. Smaller probabilities mean that you can have a nonlinear effect in terms of the gains that you might get, whereas we believe from our simulations that changes in time have only a linear effect on the increase in productivity. So this was data from the first year. We keep emphasizing that this process has to be repeatable and robust and simple and all that, so can we do it again? And so we did it again this year, and it's a different homework. This was a class in which students actually used 2 programming languages. So now we're taking a step forward. We're trying to compare 2 different programming languages. The homework is Game of Life, which I'm sure a lot of you are familiar with. It's essentially a 2D board that you have, and you essentially are just filling in cells in the board using some very simple rules. What makes it hard is that this is a parallel program, and you just don't have too much time to write this program. Similar data collections, nothing really has changed. We're just getting better at our data collection, and so we capture more runtime information now. Again, the hope was not to replay everything. I mean, it takes a long time to replay all these student codes, so we didn't want to spend time doing it. But every year it turns out that we miss some data that we want to gather, and so we end up replaying things. In this case, we spend 950 hours of time on data star just replaying all the student effort. I mean, every single compile and run that the students made. And what came out of that? Okay. Oops. So it's MPI and UPC. MPI is a message passing interface. It's sort of the assembly level of parallel programming, where you say, oh, send a message from processor 1 to processor 2, get a message from processor 2 to processor 1, or you can be fancy, you can do non-blocking things. It's very message oriented. You have to break down everything into sort of very small pieces of code and sort of worry about each section of code and messages and everything. UPC is Unified Parallel C. It sort of tries to get rid of this message passing thing and gives you a nice view of the language, gives you global arrays and sort of one-way addressing for your programming language, so you're never passing messages, you just copy things around in memory. So, question?
I'm just wondering here, it says, if I read this correctly, it says 0.002, so 0.2% of the time students skip the optimization loop.
Oh, so what happens, so actually that's a good thing you point out.
There are only 10 students.
Sorry?
There are only 10 students, is it?
There are only 10 students in the class. Now, you'd expect that you test your program, you optimize it, and then you finish. But often what happens is you optimize it, and if you look at the run to debug transition here, you're optimizing your code and you get a bug in the code, so you're back in the debug cycle. And a lot of times what happens is students are like, oh, my 2 weeks are up now, so just submit what I have. And so that represents the low probability transition from going from test to finish. There are only 10 students, so there are only 10 finished states in these codes. I mean, so that's why the numbers are so small on those. The thing to look at is that MPI and UPC are not that much different. So I'm just kind of going to flip between these two to make things a little clear of what's going on. If you look at the compile states, the time spent is approximately the same. It's 68 seconds in MPI in the run cycle, 278 in the compile cycle. Okay, UPC programmers do better with their compile timings. They're spending only 191 seconds in their optimized compile state. If we look at the times going from optimized to compile, how much time do you spend optimizing your code, editing your code in the optimized cycle? It's 883 seconds for MPI, 763 seconds for UPC. So maybe it's easier to tune UPC programs if we are to believe these models. But let's look at the all-important transitioning in MPI going from test back into the debug cycle. 92% here. 92% of the time you're not making progress. UPC, it's 95%. Okay, maybe MPI is not that bad after all. Maybe what's going on is that they're both equally bad. Or maybe it's just that these students are not good programmers at UPC and MPI because this is really their second homework and they're not used to writing these program codes in these languages. Question?
Well, there were only 5 students in each of these 2 samples, right?
That's right, and that's another
What was the variability? Could just the variability alone account for plus or minus 3%?
So the question is, so I need to repeat the question so that the guys at Utah can hear us. The question is, there were only 5 students in each class, and is this the variability across the 2 sets of students? Is that the question?
The variability within any given sample. If you have 5 students with high variability, how can you say that it's 0.95? It's 0.95 plus or minus.
Plus or minus, no, you're right. So at this point, we have avoided doing any further statistical tests. At this point, we are just aggregating numbers and taking averages, putting them on these models. We haven't, I mean, you're very right. I mean, there is actually a very high variability in these students out here. Let me get this question, and then maybe I can answer both.
Well, thinking about the time they spent optimizing is good, but we don't see what the result of the program is. Did the people who spent more time optimizing get a more optimized program?
So that's another very good question, and the answer is no. I mean, there are often students who spend very little time writing their programs, getting much faster results. I mean, so that's another problem with time Markov models, right? They do not capture this kind of information. You do not know how many times. So here's one thing I could do, right? This, I think, might answer part of your question as well. I could make this model for each student now and compare individual models. And maybe what I'd like to also do is maybe have a little number saying, student A went only 10 times around the optimized cycle, where student B did that 100 times. But maybe student A got a faster code than student B. But maybe his code failed when I scaled from 8 to 32 processors. All these kinds of things. We have all this data, I mean, and we see all these things that you say, but we haven't quite yet figured out how to put them in the model, how to reason quantitatively about that. And that is one of the reasons why I'm here to give this talk, is to get more ideas and feedback from guys here. So this is really, I mean, this is really a very nascent effort at this point. Only 2 years worth of data. I mean, we didn't even know if we could make these models. So these are sort of fresh off the, fresh off the oven kind of results here. The next step would be exactly, comparing programmers, seeing what the variability in each group is. Going back to the question about variability, we did try to make sure that the groups were equally balanced, in that there were, about the same number of engineers and computer scientists in each group. And looking at the previous homework, we kind of tried to make the groups more equal so that the skill levels were about the same.
So the students were randomly assigned to use either UPC or...
So the question is whether the students were randomly assigned to UPC and MPI. We assigned them randomly initially, but we did some swaps to account for sort of both groups having the same skill level from what we saw in the previous homeworks. This is, and the validation was that the speedups that the students got in both the groups was about the same. Although the variability was quite high. There were some people who couldn't finish the homeworks, and there were some people who were packing things into bits and getting bit level parallelism out of their codes running on each node. So conclusions. This is it's repeatable. It's systematic. We believe this is the first time that someone actually put a quantitative model trying to compare two environments. We do not have conclusions on what it means. It's too small a sample size. There's too much variability. We need more data, and we need to figure out what the right things to measure are. Not restricted to high performance computing. This is something that you could do for anything and everything, and that's something that is in the works. So Vic and I are writing a little package which would allow you to do it for Python, Perl, MATLAB, Java, anything that you want to write in. You write your unit test frameworks beforehand, and it will tell you, where you're spending your time. So, I mean, people like me who do not like to use debuggers and rather prefer print statements. Maybe even I'm writing my code using this thing and it says, oh, you're spending too much time debugging. I'm like, maybe I should really try to learn how to use a debugger after all. Printfs are not that good. Or maybe printfs are good, who knows? Methods are not restricted to the classroom. You can build up more models for for larger groups of people working together, for more complicated workflows that actually happen in the real world, people delivering real products. But the goal is that feedback-driven decision-making and development should allow us, in general, to write better programs and ship within time and budget. And I think that concludes our talk. We're open to questions.
If you have questions, and I really doubt it, but you might just have questions that are proprietary to Google, keep them at the end of the talk so it can be taken off the video. Yeah.
Question? Yeah.
So my question basically is about, I guess when you're using Markov models, you've got to encode some assumptions generally in what you pick the states to be. So what I'm thinking is here, I mean, how much do you think your assumptions about what those states are biasing your results? For example, it seems that you're implicitly making the assumption that no one ever debugs while they're optimizing, which is, or optimizes while they're debugging, which, you know, a good programmer shouldn't, but students will.
So actually that is, so you are right in the sense that our choices of states bias the data that we gather. Although I would like to point out that we do, the possibility of debugging while optimizing and optimizing while debugging is captured because you can transition between the two cycles in this model. But in general, you're right that.
So I have something to add. So you're right. The model that we have right now gives kind of a rigid structure to what we think the person is doing. We could be entirely wrong. But since we've done data capture in a nice way, since we have all the source code, we can run it again and say, you know, we give a talk and there's a person called Mike Pero who says, well, maybe you should do it like this. And you say, wow, yeah, you're right, you know. But we can actually go back and test it. And you never know, it might just be much better. So you're right, we do have probably a problem with the models, but at least we can fix it and acknowledge it. Yes, question?
So one of the things you mentioned was the time in the cycles. You can rewrite this graph as each cycle being one node and then summarize the transitions down that in that little thing. Have you done that? Do you have that data?
Repeat the question. So I'd like to repeat the question. The question is, and correct me if I don't get the question right, is collapsing the cycles into actually individual nodes and then trying to get the time spent in each cycle. And the answer is, yeah, yes, we do have the data and for doing this, but we haven't done this yet. And I think this is an excellent suggestion, and I think that would be a very good way to, so we could sort of just club the top cycle into one big node called debug and the bottom cycle into one big node called optimize and just see how much time is spent, and that gives us higher level data from this model. Question?
Were the students given a canned set of unit tests or micro benchmarks to use to get correctness of performance, or did they have to craft them themselves?
So the question is whether the students were given canned sets of benchmarks to test their programs. And the answer is, so we have 2 years of data. The first year where students did parallel sorting, they were not given a canned benchmark. They were just told that we will test, you know, we'll be the adversary. We're just going to give it like the worst case data that we can think of. Almost everyone used random data sets for their testing. And anecdotal, I was the TA, and that's what I saw them doing. The next year, we figured out it would be better if we gave them unit tests and say, you know, you have 2 weeks. These are your test cases. Just get it right on this. And that's what happened the next year. So there was more control in sort of the second year of the experiment, which allows better data capturing. Question?
So my questions are two. Firstly, what other parts of the development life cycle are you planning on including as you move forward? And secondly, was the code base that they were working on, were they working on it together or were they working individually?
So question one was about what other parts of the life cycle we would like to capture, and the second part is were they working individually or not. And let me answer the second one first. Yeah, it was the homeworks that we measured, students were in fact working alone. We do not know if they collaborated. We sure hope not. Now the first part, what other life cycle or parts of the life cycle for writing a program do we indeed want to capture? And as far as the homeworks go, I think this is okay, but we actually want to move on to larger programs where, you know, I mean, performance is really not the only criteria, how readable your code is. I mean, do you write maintainable code or, you know, or do you not? Metrics for porting, readability, et cetera.
So it's a good thing to measure. It would be great if you could measure, well, does this guy write good code when he's put in, you know, X team in Google? But the thing is, it's hard to do because you don't have any control. You don't have 5 people doing the same thing. Also, it's very hard to know what you're trying to measure. And towards that, I say it's a nice idea to have, you know, test-driven development where you have a set of unit tests, and then you can give it to different people probably working on different projects and say that, all right, all these tests are about the same amount of effort, and then compare. So I suppose it can be done, but we haven't looked into it yet.
Yep.
Okay. Actually, there's a question, but I think that this could be a very good way to measure if pair programming works.
Sorry, what?
If pair programming works, right?
So the question is, this might be a good way to actually measure if paired programming works, and I believe that this is sort of a new thing that has been recently going on, where you sort of have two people working on the same computer screen, working simultaneously on a program, and the hypothesis is that this works well, and you're absolutely right. I mean, we should use a model like this to actually quantitatively prove one way or another.
Find out for sure if XP works or not.
Yeah.
Do you have any preliminary results on that?
We do not. Do we have any preliminary results on that? No, not yet. We hope to start doing that for student projects in the class this year, and so maybe that'll yield something. Questions?
I think this is a good start for measuring productivity in the small, but will you also tackle productivity in the large?
So the question is, this is a good start for measuring productivity in the small, but would we be doing this in the large or not? It's a good question. We would very much like to do it in the large. I think we have gained enough experience from doing classroom projects, and the classroom experiments are going to keep going on irrespective, but we would really like to start doing this on larger scale projects. We have some ideas which, a lot of these things like replays are not possible, I mean, we can't replay every snapshot of, the Google search or the Google, some big project at Google. But maybe we can have plugins that actually go around querying Subversion or CVS databases, try to glean information from them and maybe take a guess at what's going on. So this is something very much that our group would like to do, and the HPCS program in general wants to do. The program was set up not for figuring out how productive students are, but for how productive highly paid DOE programmers writing weapon simulation codes are. Of course, I mean, you don't want to get these highly paid programmers writing on a questionnaire, so what did you do this hour? And, so that's how the classroom experiments started, the guinea pigs, but that's very much a goal for us to go to.
Yeah, I think it is possible to do it in the large if we sit down and think about it. I think if you write down, like an Eclipse plugin or something which gathers enough data about what you're doing, and you give it enough information, so you give it a unit test, or you give it a fair amount of stuff that it knows about your work, then it can probably tell. But that will require quite a lot of discipline in getting the framework set up.
Logical and physical design starts playing a larger role in programming in large. So how would you account for that?
So the question is, how would we capture logical versus physical design issues? Logical and physical.
Physical meaning the way files are organized.
Yeah, physical meaning how files are organized, and logical meaning the thought process, the formulating that goes on.
Java packages and C++ namespaces.
So in one of the slides, we actually said that there were several things that you could hold constant and try to measure the effects of things that change. So one thing, I guess, in this experimental setting that might be possible is not give students these harnesses that we give them, but just give them problem description and see how they go about doing these things. There might be other variation, but there might be one way for us to kind of capture people actually, are they writing modular packages? Are they writing comments in their codes? Are they, organizing their file systems well or not? I think, again, I mean, this ties in with your previous question, is that this would probably have to be on a larger scale, because in a small problem like this, these effects are unlikely to actually even show up. Question?
You said earlier that the information that the students gave you about what they've been doing during each step, you ended up throwing that away and replaying it. Did you compare back how close people got and why you think there was a difference in what people said versus what you guys think they were doing?
So the question is, were people actually that we actually, in the 2005 experiment, we did not use the data provided by the student questionnaires, and that it would have been a good idea to go back and correlate it with what we guessed as opposed to what they provided. That was very much something that we wanted to do. Our group hasn't done it. There is a group at University of Maryland that has been trying to sort of put the two together and see if students actually report the correct activities that they're doing. We didn't have enough people to do this at that point, but that's not a good reason to not do it. Another reason why we did not do it was also that we just saw we saw most of the students just hitting 1 as the reason for almost everything.
Well, another reason why I ask is because it'd be sort of interesting to know how productive people think they are, and also sort of their confidence level as they're working. Like, are they getting really frustrated with the task that you're trying to do, or not? Like, and how does that then affect the timings? Like, if someone's getting really frustrated, are they working less and less efficient, or you see what I mean? Like.
So the question is maybe a reason to do something like having a questionnaire along with these automatic inference systems is to figure out if the programmer is actually doing what he thinks is doing, or she thinks what she's doing, or if they're getting frustrated while in development, and maybe they should be going back, doing something more productive and coming back. I think that would be excellent. I mean, wouldn't it be great if your computer would just say, you're too frustrated, you're locked out?
Go get a soda.
Go get a soda or something, yeah. I think that would be very interesting.
Can you switch to the other MPI slide?
Okay, switching back to the MPI slide. So the slides are going to be put up on the internal Google network. Question?
I have a kind of related question about timing. Say, for example, that students are a bit lazy, and that you have a hidden state between, say, test and debug, which is go watch some TV or go down the pub and have a drink. How does this, how do your timing estimates handle people just taking breaks and coming back to it the next day?
It's a good question. Do we account for people grabbing soda, or going use the toilet, or going to get dinner? What we do is, if we notice more than, I think, 30 minutes of inactivity, we just truncate it. Not the best way to do it, but there's a good chance that the person wasn't at their terminal. We do have more logs being collected now, with logouts and shells and stuff, but these are more intrusive. You need system administrators and stuff.
It sounds like what you really are referring to is that you will have a programming session where people will be doing an activity and you'll have threshold where you'll cut it off, which is a semantic terminology issue that might be kind of the way you want to look at it.
Do you want to take this? Oh.
Yeah, the question is, what we are really doing is we're breaking down the workflow into time slots of some time. And Chris, was the question that, is that what we want to do?
No, I was just offering a terminology that you might really.
Oh, sure. Okay.
So the terminology of a session.
Yeah, the terminology of a session, in that we're allowing the person to work for 30 minutes at a time as a session. It's interesting. All right, thank you very much for being here. We didn't expect anyone to show up, so we're really quite pleased. Really good questions too. Thanks so much.